Okay, good morning, everybody. Hope you're having a great Saturday. Here we go. So last time, we've been following the history of electricity now for close to 300 years, and last time we really started reaping the fruits of our hard work. We saw how Heinrich Hertz discovered that there can be invisible electromagnetic waves that later on people used to communicate. Hertz made his big discovery in the late 1880s, and already in the mid-1890s, people were routinely telegraphing across the Atlantic. We also saw how the study of electricity eventually gave rise to this image, the first X-ray, 1895, just a few years afterwards. And we saw how the event that put Konrad Röntgen on his discovery of X-rays was actually something like this. People studied how electricity was conducted in dilute gases. And they discovered that if you put two metal electrodes in an evacuated glass tube, from the negative side of it, you would have these very weird cathode rays, negative side being the cathode, emerging, moving along straight lines, and casting shadows of whatever you put in their path. And so that opened up, if you will, an entirely new perspective on electricity. Because the cathode rays, as people found out, behave just like electricity. As we saw in Thomson's experiment, if you put a magnet close to them, they get deflected. They don't move in straight lines anymore, they move in circles. Just like in Faraday's old days, current flowing through a wire was also deflected and eventually made the wire revolve around Faraday's magnet. We also saw how the cathode rays could be deflected electrically. Just like in two-phase days, if you put two objects with equal charges close to each other, they would repel. Likewise here, if you put a negative charge in the top plate and a positive on the bottom, the rays would be repelled from the negative plate and would be attracted to the positive plate and the other way around. So for all intents and purposes, cathode rays looked like electricity that was flowing through vacuum instead of flowing through a wire. So there was this very big, profound connection between cathode rays and electricity flowing through a wire that was made precise in 1897 by J.J. Thomson, when he saw that in both cases, what you have actually is not an entirely independent phenomenon. In both cases, it's small little particles, each of which with a tiny mass carrying a tiny amount of electricity, and these particles can move through a wire, and then we call it electricity, or these particles can move through empty space, and then we call it cathode rays. Electricity is nothing but a stream of electrons. And so, this is the slide that we started with 3 weeks ago, and it's also, if you will, the one that we ended with last time, because our question of what is the nature of electricity has now turned into a different question, which is the one of nature of matter. You know, if electricity is some material entity, some particle, how does it fit in the grand scheme of the nature of matter? And in fact, this turned out to be a question that people asked themselves for a very, very long time. One way of asking the question is matter continuous or discrete? Even the ancient Greeks were thinking about what happened if you took a piece of matter and you cut it in half. And then you cut it in half again, and again, and again, and again. How far could you keep going? Would you at some point have something that you could not split in half anymore, or could you just continue forever? So that was really a topic of eternal philosophical debate. And before people had the tools of science to study that question, they used the tools of philosophy to reason about it. And so it was this gentleman here, Democritus, 300 BC, who had the following quote, which is actually one of my wonderful all-time favorites. By convention there is sweetness, by convention there is bitterness, by convention there is color, but in reality there is only atoms and the void. Everything is made up of small elementary pieces, and everything that we see around us just emerges as the effects from large numbers of atoms being put together. Now, so far so good. Democritus also continued to explain how the atoms gave rise to all of those, sensual expressions. He says, bitterness is caused by small, angular, jagged atoms passing across the tongue. Sweetness, on the other hand, is caused by larger, smoother, and more rounded atoms. Now, the first real hints that atoms might be something real once again came from chemistry in the 1800s. When people discovered that if they took one of Volta's batteries, as we saw, he wrote his famous letter describing how to build a battery in 1800, and very soon thereafter, people discovered what happened if you connect 2 metal pins, you put them into a jar of water, and you connect them to the battery. What you would find is bubbles forming on both sides and rising up. And if you put 2 glass tubes upside down, you could catch those bubbles. And the gases that you could accumulate in those glass tubes turned out to be nothing else except oxygen and hydrogen. But the real important hint for us here is that no matter what you did, you would always exactly get 2 times as much hydrogen as you would get oxygen. Okay, so the sort of empty volume that displaces the waters would always be 2 times larger in the case of hydrogen than in the case of oxygen. Not 1.3 or 2.75, but exactly 2 times as large. And these whole numbers also started appearing elsewhere in chemistry. People discovered that you could use electricity to split up water into hydrogen and into oxygen. And of course, the reverse was also possible. You could recombine substances. When 2 measures of hydrogen and 1 of oxygen gas are mixed and fired by the electric spark, the whole is converted into steam. Okay, you can split water up if you use electrical energy to do so. If you combust the 2 back together, you get water out, and the electricity turns into the energy of the explosion. So hydrogen and oxygen can go back in water as long as you maintain that 2-to-1 ratio. Now, one of the leading chemists of these times, John Dalton, he also noticed something a little bit more subtle than that. He said, if you take 100 grams of carbon, and you take 103 grams of oxygen, and you combine them and let them react, what you get is something else that today we call carbon monoxide, but nothing else. Okay, there is no residual carbon, there is no residual oxygen. Everything is used up in that reaction to give you carbon monoxide. Now he says something else can happen if I take twice 133 grams, so 266 grams of oxygen, and the same 100 grams of carbon. I can also react them again, and again nothing is left over, but now what I get is something different, and today we call it carbon dioxide. And he noted there's again this very weird whole number ratio appearing. 266 is exactly twice 133 and not 1.3 or 2.75. And in fact, this empirical fact that he noticed in many different reactions in chemistry, he elevated it into the rank of a law, which in chemistry is really just an empirical observation that shows up in many different places. And he calls it the law of multiple proportions. Okay, in 1804, he said such ratios of whole numbers, 2-to-1 here, 2-to-1 up here, and so forth, they will appear everywhere in chemistry. And that has a very significant underlying cause. And in fact, Dalton was very cognizant about what chemistry could do or what chemistry could not do. He says, in all chemical investigations, whatever, all the changes we can produce consist in separating particles that are in a state of cohesion and joining those that were previously at a distance. Okay, so all he says that chemists can do is, like in the case of splitting water with electricity, you separate things that were previously together, or you can do the reverse, you can combine things that you already put at a distance. Okay, these are all the changes that chemistry can ever produce. And so, he used the concept of atoms to explain why he always found these whole numbers. If you take 1 atom of A and you add 1 atom of B, okay, carbon and oxygen, you get 1 atom of C, carbon monoxide. Likewise, if you take an atom of carbon, and you take 2 atoms of oxygen, okay, in that second reaction that we looked at, you would get 1 atom of a different kind, D, that would be an atom of carbon dioxide. Likewise, in the case of water, he says, water is a binary compound of hydrogen and oxygen, and the relative weights of the 2 elementary atoms, hydrogen and the oxygen atom, are as 1-to-7, okay, everywhere whole number ratios. So his 3 main theses were the following. There are atoms, and they are elementary. Okay, there are atoms of carbon, atoms of oxygen, atoms of carbon dioxide, and so forth. And because atoms are elementary, they have to come in whole numbers. You cannot have an atom and a half. You can only have 1 or 2, or nothing in between, because you cannot split up an atom because they're elementary. And then third, the masses of different atoms relate to each other as whole numbers. And that's a separate important part. Not only can you not have half an atom, but if you take 2 different atoms, their masses are also in whole numbers relative to each other. Okay, so if you have 1 atom A, 1 atom B, B can only be twice as heavy as atom A, or thrice, or 4 times, and so forth, but nothing in between. In fact, this 1-to-7 number up here in the ratio of the mass of hydrogen and oxygen, he got it wrong. In fact, today we know it's 1 to 16, and chemists soon after, they corrected him. But it's a whole number nonetheless. And so this is the scheme that Dalton put up, and he published a book about it, of how chemistry ultimately works. Okay, and he drew pictures. He would have these symbols, each of which signified a different atom. There would be single atoms, and there would be composite atoms, and so on and so forth, and you could build up the entirety of chemistry in that way. And in his book, he would also have a table listing all of the relative atomic weights. Okay, he started with the lightest atom, the atom of hydrogen, and he would say, any other atom, I can measure its mass in units of the hydrogen atom. Okay, if you go here, for example, oxygen, he would say oxygen is 7 times as heavy as hydrogen, which today we don't, which today we know is not true, but it's a whole number. Likewise are all the other weights. For him, atoms were a building block that you could use to combine and separate and so forth, but the nature of atoms were of no significance to him as a chemist. He says, the atoms of such bodies are conceived at present to be simple. Okay, he was not interested in finding out what happens inside an atom. To him, the atom itself was already the goal that he wanted to have, because it gave him the tools to think about chemistry. And in fact, if you look at the table with his atomic weights today, some of them are close, but most of them are actually not correct. Okay, so most of the numbers that he writes here, they would be corrected later on. But the idea was a good one. So there was some regularity entering chemistry at around that time, but it was also a time of great confusion, because new chemical elements would be discovered at an extremely high rate. Around 1 new element would be discovered per year. And so in the second half of the 1800s, there would be of the order of 50 or 60 different chemical elements, and people started to wonder whether there is some order inherent in this chaos. Okay, 60 elements starts to be a bit too much to comfortably think about. And many people tried, over the years, to come up with a scheme of classifying these elements. But the scheme that finally stuck was invented, or discovered, by Dmitry Mendeleev, a Russian. And he said the following: there is an apparent periodicity in the chemical properties of these elements. Okay, I can make a table with 8 different columns, and I put all the elements that have similar chemical properties in the same column. Okay? And then he said, if I start with the lightest element, hydrogen, and then go to the 2nd, 3rd, 4th, 5th, 6th, 7th, and 8th lightest, by the time I get to the 9th, which is lithium, I end up back in column 1, because lithium is very, very similar chemically to hydrogen. Okay? So you would go through this table left to right and top to bottom as you went up in the weight of your chemical atoms, but because you would always have to jump back to the first column, you would have this periodicity in the chemical properties. And you will also notice, okay, you start with hydrogen, and then here you have oxygen. By the way, oxygen in his case already has the correct weight of 16. He already corrected the mistake that we saw before. Boron would be here, 11, and so on and so forth, aluminum. But you would also notice that there are some entries that he doesn't put a name in. He is so convinced that his system of classification is correct, because it fits all of the chemical elements, but it has gaps. And he makes the bold step of saying there are gaps, but they are there because these elements exist, but they haven't been discovered yet. And indeed, everywhere he puts a dash, because he doesn't know the name of that element, later on it would be discovered, and it would nicely fall into place and would fill in the gaps. And so this is around the time when we again reach the time of the year of Thomson's big discovery of the electron, but now from the side of chemistry. We saw last time how Thomson made that discovery. He would take cathode rays and he would use magnets to deflect them magnetically and electrically and so forth. And we saw last time how he then arrived at his big conclusion, namely the view that we have in the cathode rays matter in a new state, a state in which the subdivision of matter is carried very much further than the ordinary gaseous state. So Thomson, of course, knew about what happened in chemistry, and he knew about, if you will, the origin story of atoms and how they had taken over in chemistry. And so he was wondering, naturally, how did his electrons that he discovered fit into this picture of atoms? And as we also saw last time, Thomson from a very young age was very curious about the ultimate nature of matter. He did his master's thesis on that topic. And so he tried to come up with a view of how to put together the idea of an atom as some sort of discrete building block of matter and the existence of his electron. Now, of course, Thomson knew, many people before him knew, that matter normally is electrically neutral. Okay, we don't get electrical shocks if we touch something around us, but his electron, of course, is negatively charged because he managed to deflect it in different ways. Electrons are negative, atoms are neutral, so if you had to have electrons inside an atom, their negative charge would have to be balanced out by a positive charge. And so in Thomson's view, the atom was a positively charged sphere, and inside that sphere you would have a couple of electrons flying around, such that the overall charge of the electrons was exactly balanced out by that positive charge of that big sphere. That's what he says. We suppose that the atom consists of a number of corpuscles, okay, the electrons, he calls them corpuscles, moving about in a sphere of uniform positive electrification. So his electrons in that picture, they were not fixed, but they could sort of move around inside that sphere. But also notice the following: if an electron tried to escape that sphere, you would have a negative charge up here, and it would now feel the overall positive charge of the rest of the sphere and be dragged back in. Okay, so in his picture, the laws of electricity and the attraction of unequal charges would actually explain why atoms are stable and why electrons didn't simply fly apart and fly out of the atom. And then Thomson did the next step. As a good scientist, he said, okay, now I have this idea, this view of what could be the case, and to see if it is actually the case, I need to see what kind of consequences that would have. What properties would this structure confer about the atom? And are these properties that are compatible with what my colleagues in chemistry had found? Now, we just spoke about stability and the fact that electrons venturing outside of that charged sphere would invariably be pulled back in. But in fact, he went a bit further. He says, if I really want to have a stable atom, then I cannot simply have these electrons moving inside in random ways, because that would be very complicated. It would be very difficult for me to convince myself that it was actually stable. But what I need to do is, if I put all of these electrons on circles, on rings, and I make them rotate, then that's something that I can prove mathematically would be stable. And moreover, I can add more and more electrons on these rings, and in this way, I can naturally have states that I know are stable and contain many electrons. Okay? But then he says, wait a second, actually it doesn't work like this forever, because you cannot have an arbitrarily large number of these electrons sitting on a single ring. Again, you fall out of equilibrium and the thing would blow up. Something that he, found out in his calculations on paper. But he also found a way out of this conundrum. He said, if I want to have an atom with many electrons, I can make it stable by putting inside of that ring some additional electrons. Okay? And that meant you didn't only need to have a single ring of electrons. You could have rings that are of ever larger sizes. You can have shells, if you will, of electrons, a small one and a large one. And in this way, you could again build up very large atoms. And then, Thomson made another step, saying that, okay, now that I have some idea of how these atoms would have to look like in order to be stable, what are the chemical properties of such atoms? In other words, he made an attempt at a wonderful way of unifying the laws of chemistry as a consequence of the laws of mechanics and electricity. Both of these things you had to have because electrons are negatively charged, that surrounding sphere is positive, so the laws of electricity play a role, but also the laws of mechanics play a role because these things are moving and spinning and so forth. Can these two separate scientific topics put together explain why chemistry works the way it does? Amazing thought. And so this is how he built up his atoms, starting from fewer electrons, adding more and more and more, and then eventually having to start a new shell to keep them stable. And he said, well, look at this. This is not entirely distinct from what my colleagues in chemistry have found. They start with very light atoms. They keep adding more and more electrons. And at some point, they sort of jump back to the next row, because otherwise the atom wouldn't exist. It would not be stable. And so that jumping back to the next row and sort of making it very similar to what I had at the beginning is sort of like me starting a new shell in my view of the atom. So in his view, and this is how his model became known as, the electrons are somehow like raisins in a cake. You have this big positively charged sphere, and then you have those little corpuscles, the electrons, like raisins in the dough of the cake. And so today, people refer to his view of the atom as the plum pudding model, because he was British, and plum pudding was a very popular dessert in Britain at that time. But of course, that's a view of the atom, and it might be correct, and it certainly explains some of the things that people had found in chemistry. But of course, to really know whether it's correct, you had to look inside the atom to see what's there. And by this time, of course, the days of sort of philosophical debates about the topic have long gone by, and people now had the tools of science to look into the atom. And that's going to bring us on a sort of different storyline, and if you want to get the full story, we need to take a step back, around 10 years, back to Röntgen and his discovery of the X-rays. Now, if you recall from last time, what Röntgen discovered was that if you took one of his discharge tubes that were very widely available at the time and many people were experimenting with, he found that there would be an invisible sort of ray emitted from the far side of the tube that would be hit by whatever the cathode rays are, and as a result you would get X-rays that could propagate through materials and could light up a fluorescent screen even on the other side of the room. And sort of the wonder in Röntgen discovery was that really he did not have to make any advances in the instruments that he used. All of this was effectively off-the-shelf equipment, and many people had access to that equipment. So once he had made that discovery, there was really a huge surge of interest in studying both the rays that would be emitted as well as fluorescence itself, because it was still not very clear how the two, if anything, were connected. And this is the time when we now cross the paths with another Frenchman, Henri Becquerel, who came into the story from the side of fluorescence, or phosphorescence, because he grew up and was born into a family of very distinguished French scientists. His father, in fact, also studied phosphorescence. Okay, there are some minerals like phosphor, that's why it has the name that it has. If you expose them to sunlight and then you put them into a dark room, they would continue to glow and sort of emit this whitish light in the case of phosphor. That's why it's called white phosphor sometimes. And so his father was studying this phenomenon, and Henri himself also very, very carefully investigated the properties of the light that would be emitted and for how long the glow would last and so on and so forth early on in his career. And at around 1895, the year where Röntgen made his discovery, he became a professor at the École Polytechnique, that famous engineering school in Paris, that around 80 years earlier, Sadi Carnot was a student at, as we saw at the very beginning of that lecture series. Now, uranium also has something to do with that, but it enters the story in a totally different way from what you might imagine, because uranium salts were also phosphorescent. And so Becquerel was obviously aware of this as one of the world's leading experts in that subject. And so uranium salt in many ways acted just like that phosphorus. If you expose them to sunlight and then you put them into a dark room, they would continue to glow in the dark for a certain time. Now their light would not be white, it would be the color of the salt, which would be this sort of yellowish, greenish glow, faint glow, just like phosphorus. And so 1 year after he became a professor, here is something that happened at a meeting of the Academy of Sciences in Paris, where he was present. The president of that society, Monsieur Poincaré, had just shown the first radiograph sent by Mr. Röntgen. Okay, word reaches Paris about this wonderful discovery made in Germany by Mr. Röntgen, and even some pictures were shown around and passed around the audience in that academy meeting. Now Becquerel was intrigued, and he asked my colleague, what was the place of emission of those rays in the vacuum tube that produced the X-rays? Because he was wondering, on which side of the tube did the rays come from? And he was given an answer. I was answered that the origin of the radiation was the luminous spot of the wall in the tube that received the cathodic flux. Okay, so his colleagues were better informed than he was, and they knew that it was the same side that displayed that greenish fluorescence. This is the side where the X-rays were coming from, because this is the side that was hit by the cathode rays in that tube. And at this point, you can imagine the wheels starting to turn in Becquerel's brain, because he was very familiar with greenish fluorescent seeming light, and so he immediately was interested. I cogitated at once to search whether the new emission was a manifestation of the phenomenon that gave birth to the phosphorescence, and whether all phosphorescent bodies emit similar rays. Okay, so he made the following thought. Clearly, there were some new rays coming. The existence of these rays was linked, in Röntgen stories, with the appearance of that greenish fluorescent light, both in the tube as well as on the screen on the other side of his room. So maybe, whatever rays they are, their existence is linked to the existence of that phenomenon of fluorescence. And so he goes and he tries an experiment. He takes a photographic plate, a Lumière plate, as it was called, because the Lumière brothers were pioneers of photography in France. He took a photographic plate, he put it in an opaque case, he wraps it in black cloth, and he takes one of the pieces of uranium salt that he has lying around for his studies on phosphorescence. And he exposes it to the sun. Photographic plate is wrapped so it doesn't see the sunlight. He puts it in the sun to start that process of phosphorescence in the uranium salt, because he thinks if the uranium salt can be made to phosphoresce, it would also produce these rays that Röntgen had found, and they would go through the black cloth and sort of show up on the photographic plate. After developing the photographic plate in the usual way, one observes that the silhouette of the crystalline crust appears in black on the sensitive plate. And indeed, after taking it back into the room, after sitting at the sun for a while, developing it, you could indeed see the black outline of that salt that he put on it. Wonderful. But then he says, I will insist particularly about the following fact, which seems to me quite important and beyond the phenomena which one could expect to observe. Here's what he says. The same crystalline crusts, same salt, arranged the same way in the same conditions and through the same screens, but kept in darkness, still produce the same photographic images. Okay, so exposing the uranium salt to sunlight wasn't in fact necessary. And the same thing he would find after developing the plate. So whatever gave rise to these images, it was not about the sun, it was also not about phosphorescence. So this is an entirely serendipitous discovery. In fact, the way it went was that he tried to repeat his initial experiment where he put it out at sunlight because he wanted some more results to show in the academy meeting the next day. But it was a cloudy day in Paris, and so he didn't really get a lot of sun exposure on that day. But he still decided to develop the photographic plate. He put it back in, he cut it short. What he expected to see, of course, was a very, very faint image because there was not really a chance for the salt to phosphoresce at that time because there was no sun. But in fact, he found the image to be exactly the same and exactly equally strong as on a very, very sunny day. And this is when it struck him that whatever I have in front of me here has nothing to do with phosphorescence. In fact, he pointed out these effects that he observes have a great similarity indeed to the effects produced in the rays studied by Mr. Röntgen. So something about the stones, about the uranium salt, and nothing about phosphorescence. Now, these are very turbulent days in the sense that many things happened, and this is how our next hero enters the stage. Maria Sklodowska, born in Poland, in Warsaw. Here she is with her sister. And these two sisters, they made a pact. Women were not allowed to study at universities in Poland at that time. So her and her sister agreed on a deal. Her older sister, Bronislava, she would go abroad. She would go to Paris first to study there, because this is where women could, in fact, enroll in universities. Maria would work at home as a tutor, teaching students, and would send her most of the money so she could support herself. And then once she was done studying, they would flip roles, and so Maria would get a chance to go to Paris. And this is what they did, and this is how Maria Sklodowska arrived in France in around 1891, okay, just after, in fact, the Eiffel Tower was built as a result of the World Exhibition that took place in Paris in 89. She rented a small room in the Latin quarters, which is where the famous university, the Sorbonne, was located. Very small room. And she put all the effort, all the energy that he had into her studies. She was often cold. The room was very poorly heated. She didn't have a lot of money. She was often alone because she focused exactly on nothing else other than studying physics. And this is how, a few years after she arrived, in 95, she met a person who was equally passionate about science, a Frenchman, Pierre Curie. And they got married in 1895, and Maria Sklodowska became Marie Sklodowska-Curie. Now, who was this Pierre Curie? he was already an established scientist by the time they married. In fact, he already had 2 major discoveries to his credit, one of which he made with his brother Jacques. Okay, in the 1880s, so around 20 years before that, they discovered something that they called the piezoelectric effect. So here's what it is. Imagine you take a crystal, like a quartz crystal, looks like window glass, and you put a force on it from both sides, you push it together, and what would happen is that one side of the crystal would become positively charged electrically, the other side of the crystal would become negatively charged. And so if you connected 2 wires and an electrometer to both sides of that crystal, pushing it would make the needle of the electrometer move. And that's a discovery that will be very helpful, as we shall see soon. And then just at the time that they got married, he made the second big discovery, which was that if you took a magnet, a normal permanent magnet, and you heated it up over a gas flame, that magnet would actually lose its magnetism. It would just be a dead piece of mineral. It would not be magnetic. If you let it cool down, suddenly the magnetism would reappear at a very well-defined temperature, which today is called, to his honor, the Curie temperature. So in 1895, they were just enjoying their honeymoon. In fact, both of them were very fond of long bicycle rides through the French countryside, so this is what they did. In 1896, Marie was just finishing her degree, and she was looking for a topic for her doctoral thesis. Now, 1896 was the year that Becquerel had his serendipitous discovery of a new kind of ray, not similar to Röntgen's rays, but coming from a piece of mineral. And so it was natural for Marie, who was very intrigued by this, and as a young, ambitious scientist, decided to plunge headfirst into the study of these new kind of rays. So she was at the right place at the right time. And the problem that she picked for herself was the following. Now we know that there are these rays, but can we measure them very, very precisely? And if so, can we learn something from these precise measurements? So how can we quantify the strength of Becquerel's radiation? And in fact, the principle that she made use of in doing that is a deep connection between these radiation and electricity that people had, in fact, already pointed out soon after Becquerel's initial discovery. And that's the following is the connection. Now, a while back we saw that in a Leyden jar, we can store a large amount of electricity, and we do that because there is a way of having 2 metal plates separated by an insulator, glass in this case, such that the inside would contain positive charge and the outside would contain negative charge, and that would be a reservoir of electricity. Okay, that you could call it a cylindrical condenser. Condenser because it condenses all of the electricity into a small volume, and cylindrical because that's what it looks like. And in fact, you could make the same in different arrangements. It doesn't need to be a bottle or a cylinder. You could also just have 2 parallel metal plates that you put next to each other, and you charge one of them positively, you charge the other one negatively. Would also be a storage of electricity, a parallel plate, condenser. And now the following is the fact that people discovered, in fact Becquerel himself was aware of this, is if you now put some of this uranium salt inside that parallel plate condenser, in between the 2 plates, the condenser would start to discharge as a result of that radiation. Slowly, but it would discharge. In fact, the Becquerel rays, as they were called back in the day, they are ionizing rays, which meant that whenever some radiation hit something in the air, we'll see in a second what that means, it can produce a negative charge and a positive charge at that location where that ray was sort of intercepted by the air. And now it's clear what happens. The positive side, the positive particle of charge would be attracted by the negatively charged plate, and that negative charge would be attracted by the positively charged plate, and so that's where they would move, and they would cancel out some of the charges that were stored on that plate. And now suddenly your condenser stores less electricity than it did before. And so if you keep it going for a while, the charge would gradually disappear, and the condenser would be discharged. Gradually. It's a very small effect, but it's an effect nonetheless that you can make use of if you want to measure the intensity of the radiation. Because the quicker the condenser would discharge, the more radiation there had to be. And this is the experiment that the Curies did. And they had to solve several different problems when doing that, because they wanted to do an extremely precise measurement. So the first problem you need to solve is, how do you charge up the condenser? Imagine you have to charge it up to a very, very precise amount, so then you can monitor how it discharges. And this is now where her husband's, Pierre Curie's, background in piezoelectricity came in handy, because if you take one of his crystals and you suspend it, and you put a weight down there, you can have a very, very precisely controlled weight, and that would generate in the crystal a very, very precisely controlled amount of electricity. And then they would connect that crystal to the condenser, and this is how they could put a very well-defined charge on the condenser. Okay, first problem solved. Second problem, now that you have charged it up, how do you measure the discharge? Okay, now you say, okay, it's fine, it's easy. We have already seen how Alessandro Volta invented the electrometer. Okay, 2 gold leaves that sort of spread outwards if they're being charged to the same amount. So, I can use that. I can just take my electrometer device that, Volta had invented, even Thomson had used, a much more precise one, and I connect it to one of the plates of the condenser, and then I can monitor how over time, slowly, the gold leaves move back down together. And then the third problem was, once I had put the experiment in this situation, I put the probe in, okay, I put my uranium salts in, how do I then perform the actual experiment, once that process of ionization and discharge had started? Well, it's easy in hindsight. You put in the material within the parallel plate condenser that has been charged up, and you just wait. You have your stopwatch and you time it for as long as it takes to reach a certain level of discharge. Okay, and then you stop the stopwatch. Gradually the charges disappear and you keep your eye on the clock. And then third, once it has been discharged to that specific location and you've measured the time, you put in some more weight to charge it back up to the original location, the original amount of charge in the condenser, and you can start the same process again. Okay, and you can do that repeatedly, and then you can make an average of many such runs, and you get a very, very precise amount, a very precise measurement of the time that it took that amount of material to really discharge the condenser. Now, the real experiment you can still see if you go to Paris and you visit the museum. Here is what it looked like, and here is the two of them in their lab, which was little more than a closet at the university at that time, performing that experiment. And in fact, I want to point out all the elements because this is a beautifully designed apparatus. So the real plate condenser is here, and you can see it's nothing more than 2 parallel aluminum plates, and there is even a sample of that uranium mineral inside. That's what measured the radiation, and today we still use that very same principle as a means of measuring radiation. Today we call it an ionization chamber. Okay, it's a chamber because you enclose it, and it's an ionization chamber because it measures the ionization by discharging that capacitor, that condenser. So that's that part. Then where is their piezoelectric crystal? Well, it's back there. In fact, you can see the crystal up here. It's transparent, so it doesn't really show up nicely on the image, but it's held in place by that brass clamp at the top, and then you can see here there's the plate where you put the weights on the other side, and you can add additional weight or you can take off weight just to keep it in balance and generate the right amount of electricity. Then they had to have the electrometer, and the electrometer was here, and it also had to be exquisitely precise. And it is not a simple, gold leaf electrometer like it was in Volta's days. It was a much more sophisticated one. There was a needle inside that would turn, and the needle was connected to a small mirror, and there was a light source over there that projected some light onto that mirror, would bounce off the mirror and hit that ruler. And as the capacitor would be discharged, the light spot would start to move slowly around that ruler, and you could read off very precisely where it was. And so this is Marie Curie performing that experiment. You can see her hand is on the stopwatch, her gaze is fixed on that ruler. Here is from the other perspective, here's the clock, here's the weight, here's the ruler, this is what she needs to look at. It's a very slow experiment because you had to sit there extremely attentive, watching everything for a very long period of time. But they managed to pull it off, and they managed to investigate several different materials, and they put everything together in a table. Okay, all the different minerals they investigated, and what they found is that there's 2 types of minerals that are particularly active in the sense of producing the strongest effect, and they are the ones containing uranium or thorium. I was struck by the fact that the activity of uranium and thorium compounds appears to be an atomic property of the element uranium and of the element thorium. Okay, here's what she meant by that. The activity is not destroyed by either physical changes of state or chemical transformations. Okay, so now she has these materials that produce that effect that they associate with the radiation being present. But no matter what I do to those salts, I can grind them up, I can grind them into powder, I can dissolve them chemically in acids, the radiation would not change. The level of radiation would not change. So whatever I did, either in sort of physically changing its composition or chemically changing its composition, had no effect whatsoever. That meant that whatever is producing the radiation would not have anything to do with chemistry or the physical composition of the material. It had to be an atomic property, as she recognized. She recognized something else, which was that there's two kinds of minerals, namely those of uranium, pitchblende and chalcolite, that are much more active than uranium in its pure form. Okay, they were aware that these minerals contain uranium, but they were much more active than uranium itself. And that fact, indeed, is very remarkable, and it leads to the belief that these minerals may contain an element which is much, much more active than uranium itself. There was uranium in there all right, but to explain the amount of activity they observed, there had to be something else. And they set out to find whatever it is that was hiding inside that piece of black rock, that pitchblende. And it was also Marie Curie who coined the term radioactivity, because there was radiation involved and it produced activity in their experiment, so it was a sensible name to use. So the question became, is there more than just uranium? And they set out to find if there is such a thing in that mineral, and it was now a problem of chemistry. Because they had that mineral, they needed to break it down and find whatever chemical elements it contained beside the uranium. We have sought to isolate that substance, chemically, that substance in pitchblende. An experiment had just confirmed the preceding conjectures. Okay, so here they are at work. Looks like a chemistry lab because that's essentially what they're doing. They're grinding up their minerals, they're dissolving them in acids, and they're performing chemical separations of different kinds of materials. They're trying to extract whatever gives the radiation, and they try all the possible ways in which they can extract known substances and known elements, and they can check with their radiation measurement if that activity follows their extracted part or if it stays behind in sort of the big pool of mess that they had started with. And so in this way, they could slowly extract and find out what it was that was producing that radiation. We have treated it with acids and have treated the solutions obtained with hydrogen sulfide. It's a long and arduous process. But at the end, they come to a conclusion. We believe, therefore, that the substance which we have removed from pitchblende contains a metal, not yet reported, close to bismuth in its analytical properties. Because they are having a chemical process in which they can try to extract something, they can only say this is whatever is producing that activity, it has to be similar chemically to this other element. Because I know that I can extract this other element in this chemical way. Okay, and in their case, whatever meant extracting bismuth would also produce the largest amount of radiation, if you will, extracted from the original compound. If the existence of that new metal is indeed confirmed, we propose to call it polonium, from the name of the country of origin of one of us. She was very appreciative of the fact that she could have a foothold in France, but she was also homesick for a very, very long time, and she was very appreciative of the fact that Poland was her home at the end of the day. And so this is why she named that new element after her country. And here it is, still in the periodic table, polonium right next to bismuth, as they had pointed out. Very, very similar chemically to bismuth. But is there something else? In the course of these researches of extracting polonium, we have found a second substance that's strongly radioactive and entirely different in its chemical properties from polonium. Okay, so that pitchblende that I started with, their raw material, turned out to be a treasure trove of new things. Not only was there polonium, there had to be something else, okay, even more active than polonium. We believe that the new radioactive substance contains a new element to which we propose to give the name radium. And they name it radium because it's very strongly radioactive. So strongly radioactive, in fact, that they could in fact know that it was not polonium. And there it is indeed, in the periodic table, radium, right next to barium. And again, this was a long and arduous process that by now they did no longer in a small closet at the university, but, if you will, in a barn. Out in the suburbs of Paris, that was given to them free of charge because nobody bothered to use it because it was raining through the roof and everything. It was not a scientific laboratory. And that made all of these extraction work extremely challenging and arduous chemically. And it was hard manual labor. Sometimes I had to spend a whole day stirring a boiling mass with a heavy iron rod nearly as big as myself. I would be broken with fatigue at day's end. Took them several years to extract a quantity of radium that they could use to study, chemically or as a metal later, just because radium was so extremely rare. They had to work their way through several tons of pitchblende to even get a quantity that would be substantial enough to do experiments with. They still managed to know that there is radium because it's just so exceedingly radioactive. So even a tiny quantity in a large pile of material would be enough for them to pick it up because of their precise instrumentation. Radium was their big discovery. And very soon, that discovery, as we shall see, turns into a tool for science. And the person who is deeply associated with that is Ernest Rutherford, from the other side of the world. He grew up in a small town of Nelson in New Zealand. And he studied there initially, but at some point, he got awarded a big scholarship by a British commission. Okay, that was his ticket overseas because that scholarship allowed him to pick a group at any university anywhere in the world, and he would be able to go there and work with them. Now, initially, he had planned to go to Germany, because in Germany, there were the big names, Heinrich Hertz and Helmholtz and all of those pioneers of electricity. But in fact, before he could decide and commit to going to Germany, he learned that many of those distinguished scientists had just passed away. And so he redecided, and he decided to go to the UK instead. And he came to Cambridge, where he studied under J.J. Thomson in Thomson's lab. Now later on, and this is the time when we meet him, after finishing his studies in Cambridge, he moves to Montreal. He moves to Canada, where he takes up a professorship at McGill University. And what he does there, knowing of course of the developments in France, is to study in more detail the radiation from uranium. And he performs radiation measurements according to what was already called the Curie method. Okay, exactly what we discussed before. You had a parallel plate condenser into which you put your sample of material. You charge up the condenser. In this case, he had a battery connected to it. And then you had an electrometer to monitor the discharge of that condenser. Now, the Curies used that setup to compare the activity from different kinds of materials. What Rutherford did was to study the properties of these rays from one material, which in this case was uranium. Now, to study the origin or the nature of these rays, he asked himself a question. So now I know that uranium produces these rays, but what do I need to do to absorb them or to shield them so I no longer see them? And he goes and he puts thin sheets of aluminum to cover his sample of uranium, one after the other. And he measures very carefully how the radiation would go down, the level of radiation would go down as you added more and more and more shielding material. So here is the form he summarized his results. He counted the number of aluminum sheets. These would be very, very, very thin sheets, about 0.0005 centimeters for one sheet. So you could have 10, 20, 30, 40, or even 50 of those thin pieces of aluminum stacked up on top of each other. And for all of those different ways of arranging the aluminum, he measured the intensity of the radiation that would still be visible to his instrument. And he would see that it would drop off very, very quickly at the beginning, but then there would be something that remains. And that, that thing that remains is persistently there. So even if I go from, 20 all the way to 50, it's effectively at the same level. Okay, so there is something that is different about the left-hand side, where just a few parts of that aluminum can shield up most of the radiation, but there's something that remains, and that thing that remains is a lot more pesky. It stays there. I have a very difficult time shielding it away. And he used that to conclude the following. There had to be more than one kind of rays. Okay, he says, these experiments show that the uranium radiation is complex and that there are present at least two distinct types of radiation. Okay, so he says what's going on is the following. I have my uranium and I have my aluminum, and there is one type of ray that's very readily absorbed, which will be termed for convenience the alpha radiation. Okay, it's that alpha radiation that's blocked out first. Even with a few sheets of aluminum, most of it is gone. It doesn't go through. But then there is a second component, which is the one that remains. The other, that's of a more penetrating character, which will be termed the beta radiation. Okay, the red one, it manages to go through many sheets of aluminum. And even if I stack more and more and more of them, I will not be able to absorb it entirely. So the question, of course, is, now that things start to look more complicated than they did at the beginning, what is the nature of these things? What are the alpha rays made of? Now, Rutherford knows about what Thomson did to figure out what the cathode rays were made of. he tried to deflect them to learn about their electrical charge. And so Rutherford does an experiment very, very similar to Thomson's. He tries to deflect his alpha rays. Now, where Thomson had sort of the easy goal of producing cathode rays, producing electrons, simply by connecting electricity to that plate of metal inside the chamber, Rutherford had to have a source for his alpha particles, and he used radium as a source for alpha particles because radium was a very, as we saw, radioactive material. It produced many alpha particles for him to work with. And the alpha particles would enter his chamber, where he would have an ionization chamber to measure how many of them he had access to, and then again he used the magnet to see how many of them he could deflect away, to prevent them from entering the chamber and be measured. Now, I want to point out a few facts, that this is not an easy experiment to make, and it took him many tries and more and more beefy equipment to finally succeed. But he did succeed, and what he found is that the direction of deviation in a magnetic field of these alpha rays was in fact opposite in sense to the cathode rays. Okay, so while Thomson established that the cathode rays are electrons that are negatively electrical charged, the alpha rays here consisted of positively charged particles because they moved in the other direction, away from where the cathode rays would bend. And in fact, he had to really step up his game to arrive at that conclusion. Even with the largest electromagnet that he had in the laboratory in Canada, I was only able to deviate about 30% of the alpha rays. I was, however, enabled by some engineers in the department to make use of the field magnet of a 30 kilowatt Edison dynamo. Okay, this is when large amounts of electricity start being involved. And also, and that's the most amazing thing to me, this was just 2 or 3 years after the Curies had discovered the existence of radium. And already here it was being put to use as a tool for research. In fact, this is a very special sample of radium. That sample, of greater activity than that normally sold, was obtained through the kindness of Madame Curie. So she sent him a large sample of radium for him to do his experiments. There was no other way at that time to really get his hands on a source with the activity that he required. And so, by 1903, this is the picture of radioactivity. There were the alpha rays, positively charged, very easily absorbed, and they turned out to have a very high mass over charge ratio. Okay, so people imagined them as very heavy, sort of little billiard balls that carried a lot of mass, but did not really carry a lot of electricity in relation to their mass. Then there were the beta rays, which were negatively charged. They're more penetrating, as we saw, and they had a small mass over charge ratio. In fact, Becquerel, after his initial discovery, established that these beta rays are not only similar to the cathode rays, but they are also literally cathode rays. They are made of electrons. And then there was a third kind of radiation that entered the game, this one called the gamma radiation, that is even more penetrating than beta and can go through even, pieces of heavy metals like lead, and it's uncharged. You cannot deflect it with either magnetism or with electricity. And that discovery of gamma rays was made by another French person, Paul Villard. Now, around that time, Rutherford received an offer that he could not really refuse, and that was an offer to move back to the UK and take up a professorship at Manchester. Now, he was promised access to a much larger laboratory with much better equipment than what he had access to in Canada. So to Manchester he would move, and he would work there with two people that turned out to be very important. One of them is a lab assistant from Germany who was hired by his predecessor and who he managed to stay on and work with him, Hans Geiger. And there was also an undergrad student at that time, Ernest Marston, who decided to work with them as well. And the first impression that he got of life in Manchester turned out to be a very positive one. Everybody seems jolly and anxious to help, and I find a most enjoyable absence of convention. I find the students here regard a professor as little short of Lord God Almighty. It's quite refreshing after the critical attitude of the Canadian students. So things were starting off well in the UK. And him and Geiger went on to develop new instruments. Because Rutherford knew, because of the experiments he had done in Canada, deflecting alpha rays and measuring them with an ionization chamber, as good of a tool as it was, it could not measure individual alpha particles. It could only measure a large number of them at a time, some sort of continuum measurement. But what they wanted is to count the alpha particles, 1, 2, 3, 4. And so him and Geiger, they go and build, or they invent, an electrical method of counting the number of alpha particles from radioactive substances. So here's the device that they came up with. It's a long cylindrical vessel that would have a little window at the front through which the alpha particles could enter. Okay, it had to have a window because if you put aluminum there, it will already shield the alpha particles. You really had to have a hole, if you will. And then inside that vessel, the alpha particles would ionize in much the same way as we saw in an ionization chamber. But their chamber was special because it had some source of amplification built into it. And so that small little, imperceptibly small, in fact, amount of ionization would be amplified to a degree that it could actually be made audible. Okay, and this detector survived until today, and this is why you associate a Geiger counter with this clickety-click noise, which is in fact counting individual ionization events that are amplified. Now what they found was that their detector didn't sometimes work very well, and they were very puzzled. And they managed eventually to trace it down to the following fact. Sometimes the alpha particles entered and ionized, and the detector would register, but sometimes they seemed to sort of hit something and then be bouncing back out of their counting chamber, and they would not be registered. But they wanted, of course, to detect everything and count everything and would not want to have single occurrences where nothing emerged. So what was going on? They believed something was causing the alpha particles to really make a kink and to be scattered out. And so they tried to see under what else, which other circumstances these anomalously large scatterings could emerge. And in 1909, they started with their first experiments. They put a radioactive source emitting alpha particles up here. They put a little fluorescent screen down here, which they could look at through a camera or an optical microscope. And they put a thick lead plate in between the source and the device, so they could not see any rays coming directly at it. They could only see those that, if they put a metal plate next to it, would bounce off the metal plate and then hit the fluorescent screen. Okay, and in fact, they did observe something, but only if that metal reflector was held in place. And so scattering, in fact, was possible. These alpha particles could change their path instantly across very, very wide angles, which was a bit surprising because these particles were very heavy. And so, you had to have a mechanism that managed to suddenly change the direction. And so by 1913, they tried to really see what was going on, and they tried to simplify their apparatus. So instead of putting a thick metal plate as that reflector, they tried with lesser and lesser and lesser amounts. But the principle was the same. They had a source of alpha particles, they had a fluorescent screen and a microscope through which to look at it, and in between they put some material. But instead of putting that thick metal plate in there, they now put a very, very thin gold foil in there. The thinnest thing that they could get their hands on, gold foil. And then they had the fluorescent screen, and it was mounted so it could rotate, so you could move it around and see how many of those incoming alpha particles would emerge in a certain direction. And what they would find, in fact, is the most marvelous thing. Some of these alpha particles would be even scattered backwards, and fly back out in the direction that they came from. So here's a photograph of that experiment. You can see the foil in there. There's the source, and there is the microscope through which to look at the fluorescent screen. And Rutherford, he says, it was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and the shell came back right and hit you. Because that's effectively what was happening. Those heavy alpha particles fired at insane speeds and kind of a thinly gold foil and come back right back. So what was going on? In fact, it was Geiger and Marsden who did the experiment, but it was Rutherford who thought hard about it and found a way to interpret what he saw. And that is the following. He says if Thomson's view of the atom is really correct, with a large positively charged sphere, and then the electrons or corpuscles inside, and this plum pudding, and I had an alpha particle, if this alpha particle encountered the atom, which would in this case be an atom of gold inside that foil, it would sort of be attracted a bit this way and a bit that way, because there's all of these positive and negative charges sitting around the same space. It would sort of wiggle its way through and then emerge again, but at roughly the same angle. He said the only way that you could have an alpha particle come in and then re-emerge and come back out in the direction it came from was if you had a separation between the positive charge and the negative charge. The negative charge of the electrons and the positive charge of something new that had to be very, very heavy and very, very small. Otherwise, these heavy and fast alpha particles could never be persuaded to turn around and come back out. So Rutherford interpreted the results of the experiment by Geiger and Marsden as the atom having a nucleus, something that's very heavy but exceedingly tiny. And again, just like Thomson had done and like any other good scientist would do, he followed through everything quantitatively. He calculated if that assumption would lead to the result in the experiment, and in fact, it managed to describe it quite accurately. Now we reach 1914, and this is when World War I kicks off and really, science grinds to a halt. Madame Curie, at that point, having received 2 Nobel Prizes, invests all of her prize money in French war bonds and organizes a mobile X-ray unit on a truck, and she drives up and down the front lines to help, care for the wounded. In Britain, Rutherford and J.J. Thomson, both of them would serve on a physics board of the British Admiralty to try to come up with ways to detect U-boats and help defend the country. But of course, there's a big question that lingers in people's minds, the war effort notwithstanding, and that is the question of, now that we have a nucleus in the atom, what is it made of? And Rutherford says, if the alpha particles can really collide with the hydrogen atom, instead of gold, you put hydrogen there, what can happen is the following. The hydrogen atom has a nucleus of itself. It has a single electron because it's the lightest atom. If an alpha particle comes in and hits it, that nucleus, he called it an H particle, could also sort of be hit by that alpha particle and start moving, very, very quickly. And in fact, these H particles, in such a collision, these H particles would look very different in an experiment to what the alpha particles looked like, because these H particles, the nucleus of the hydrogen atom, they would be able to travel much further than the alpha particles could before they would stop or be absorbed. Okay? And so, that's what they did. In fact, they found something even more puzzling, which is if you substitute nitrogen with hydrogen, okay, this happened now after the war, 1919, you take a vessel, you fill it with nitrogen, which is very easy because nitrogen is around us in the atmosphere, and then you bombard the nitrogen with alpha particles, you would see exactly the same result. Again, you would have H particles, and in fact, a much larger number of H particles than you got in the case of hydrogen. Okay, so it looks like, and this is what he concludes, we must conclude that the hydrogen atom, which is liberated in this experiment, in fact formed a constituent part of the nitrogen nucleus. Okay, so there is something that looks like hydrogen inside the atom of something totally different, namely nitrogen. And by now he has so immersed himself into this that it starts being his second nature, and he has some intuition for what's going on. And in fact, he goes on, considering the enormous intensity of the forces brought into play in such a collision, it's not so much a matter of surprise that the nitrogen atom should in fact suffer disintegration. Okay, so he has the right picture in mind. The alpha particle comes in, hits the nucleus of nitrogen that contains many H particles, which then come flying out, and he could detect. So, the nucleus of hydrogen atom is in fact not only a particle of its own, he called it the H particle, today we call it the proton, but it occurs everywhere else other than hydrogen. Okay? In particular, it occurs in nitrogen, which is much, much heavier and has more of these H particles than hydrogen does. And so, the atom turns into something very different from what it was at the beginning. Not only can you have hydrogen and nitrogen, both of which are made up of protons and electrons, and nitrogen, much heavier than hydrogen, would contain more protons and more electrons. But in fact, by adding more and more electrons to that picture and more protons, you could indeed build up all of the elements in the periodic table. Okay, so nuclear chemistry starts being a thing. Not only can you change hydrogen and oxygen into water, you could also play games with the nucleus, because there was radioactivity. And people knew that if you started up with polonium, which is down here, and you let it decay and it made an alpha particle, it would turn into lead. It would move over here. Likewise, if that polonium emitted a beta ray, it would move right and turn into astatine. So not only could you change atoms into different compounds and chemical substances, you could also really just sit and watch and see the nuclei rearrange themselves, just like in chemistry. But that was also very puzzling because of the following fact. Imagine you start up with uranium and you wait for it to decay, which it would also emit an alpha particle. It would turn into thorium. It would be there. But thorium, as the Curies found out, is also not stable, and it could also emit a beta ray, you end up at protactinium, which was also not stable. You made another beta ray, and you end up back at uranium. Okay, so you have gone through in a circle. You started with uranium, you ended with uranium, but you also got one alpha and two beta particles at the same time. So what was going on, right? I mean, this cannot just keep going all the time. So how was that uranium at the end different from the uranium at the beginning? In fact, it was again chemists, in this case a British chemist, Francis Aston, that collected more hints. Okay, by this time, people had also discovered that there seemed to be two kinds of neon. Okay, not only seem to be two kinds of uranium, but also two kinds of other atoms that have slightly different masses. But both of them are bona fide neon. So what was going on? So how is this possible to have two versions of the same atom, right, that are heavier than the other? Now imagine how you could produce something like this. You take an atom and you try to make it heavier by adding an additional proton and adding an additional electron. Right? But by doing that, you in fact turn it into a different element. You turn it into a heavier element, all right, but having different numbers of electrons would make it chemically distinct. So it's no longer neon. You would not turn it into a heavier version of the same element. You would turn it into something else. So, what has to give? Something is wrong. In fact, people suggested that maybe you didn't have to add the electrons and the protons, in different places. Maybe you had to have both an electron and a proton sitting in the nucleus together, right? An electron and a proton taken together would be electrically neutral, and you could imagine having them in the nucleus, which would make the nucleus heavier and heavier, but it would not change at all how the element looks like from the perspective of chemistry, right? So it was all right. But you had to have something neutral to play that role. And in fact, a new neutral particle was discovered in the 1930s by a group in Britain and a group in France, Frederic and Irene Joliot-Curie. By the way, Irene is Madame Curie's daughter, who also turned out to be a great scientist and won a Nobel Prize. And they did the following experiment. They noticed that if you took polonium or some other source of alpha radiation and you let it impinge on a thin foil of beryllium, which looks very similar to aluminum foil, you get something new. Okay, you get a different source of radiation that you could measure, and it was extremely, extremely penetrating. The intensity of that radiation remained the same even when as much as 2 centimeters of lead were inserted. Okay, much more so than even the gamma rays. Now it goes on. In order to explain the great penetrating power of that radiation, we must assume that that particle that carries the radiation has no net charge. Right? Because if it had some net charge, sooner or later it would encounter a nucleus and be scattered back out. It could not simply keep going, as it was seen. So the question was, there was a new neutral particle. The question was just, which kind of neutral particle was it? That was, Chadwick's big question. Was it really a proton and an electron super tightly bound together, held together by their electrical attraction, so as to appear neutral and simply be able to fly right through? Or was it, something new that was also neutral but did not contain a proton and an electron inside? In fact, Chadwick himself gave the answer a few years after in a very, very elegant way by measuring the mass of that new particle. And it turns out that it's larger by just a tiny amount than the mass of the proton and the electron taken together. So whatever was inside the neutron, it could not have been an electron and a proton because that would not have the correct mass. So there was something new. And that means that something new had to have its place in the atom. So not only did you have hydrogen and nitrogen, containing different numbers of protons and electrons, you could have different versions of each element that differ only by having different numbers of neutrons inside the nucleus. Okay, and in this way, that paradox of going in circles and ending up where you started disappears. You don't end up where you start, you end up with a version of uranium that has fewer number of neutrons, the remainder sort of being converted and sent out in alpha and beta form. And so, we have come quite a long way, starting from Dalton's view of the atom in 1808, which appeared to be simple, and he has all of these different symbols for them. A century and a half afterwards, atoms turn out to be everything but simple. They're not simply, little circles with certain symbols inside. They are themselves composite objects containing protons, neutrons, electrons, in a very finely balanced way. So that was, again, a huge change in our worldview from that picture to here. And as we've seen in the past, huge changes in our worldview usually come with big consequences. And these are consequences that we will explore next time. Thanks a lot. Yes?
Thompson came up with a shell model. Had 8. Is that number 8? 8 photons. Is that a consequence of its mechanical stability, or is that just something you know from the Bohr model?
Very good. So you're talking about 8, as in 8 columns in the periodic table. Yes.
Was that something he got from stability measurements, or was it?
Right. So even right. Very good question. So the question is, how in this case, if you go all the way up to 8, that atom here chemically it turns out to be a lot stabler than an atom at the beginning. Right. Lithium, for example, is very reactive, while helium, which is over here, is not. And so, in fact, already Thomson tried to explain part of this in his model, and it sort of makes sense, which is to say that, in his worldview, you get heavier and heavier elements by adding more and more electrons, and eventually you would have to start a new shell. But if you start a new shell initially, that new shell that you have would only have a single electron inside. And if that's an outer shell that you have to start, that single electron could very easily be sort of ripped out of the atom.
So did he get this from Mendeleev, or is that a result
So
of calculation?
Very good. So so this is a result that he got out of his calculation. So he calculated a quantity in chemistry called the electronegativity, which is effectively just a measure of how reactive a certain substance is, or how easily one of the electrons could be used for some chemical process. So that's what he managed to calculate, and he found some periodicity resembling the one that chemists already knew about, but the details didn't match. Okay, there's something that feels correct, but that's wrong in the details. But it was a very encouraging first step. This was, being able to do this was unheard of, right? Trying to go underneath chemistry and explain it, by something else,
Preceded Bohr's model.
Right. Yes. Yes. Go ahead.
Why do so many chemicals end in IUN?
Very good question. I don't know. No idea. I guess somebody started it and then people kept going. Maybe there's a better answer. I hope there is.
Where does the Bohr atom idea come in this?
It comes in much later. Yeah. So the Bohr atom, so the sort of the window into the study of the atom, in fact, also came from the interaction of light with atoms, because you can imagine, and this is also something that opticians, in fact, have done for a very long time. Even Isaac Newton had done experiments with prisms, right? And he discovered that you could split up white light into all different colors. So people started playing with light and how light interacted with materials, and so they discovered that individual gases would have a very distinct light signature. Right? If you send light through a certain gas, or if you took light from a certain source and you split it up into its different colors, what you would get is, if you will, a fingerprint of that material. In fact, this is what Becquerel studied in great detail when he was investigating that whitish light that comes out of phosphorus. He split it up into its spectral components, and these are the lines that you can see, taken from his PhD thesis. And people realized already then that different chemical elements had these lines with different strengths in different places, different colors, if you will. And so people recognized this, rightfully so, as a very powerful diagnostic tool to learn about what was going on inside a certain sample of material. And they collected these spectral lines for all the different materials that they could feasibly do an experiment like this with. In fact, that was also one of the ways the Curies proved that radium was something new, that was not just a chemical element that already existed. Because it had lines, radium showed lines in places where no other known chemical elements had them. Okay, that was a very convincing argument to make in favor of the nature of radium as a new chemical element. And so over time, as people got more and more proficient at making these measurements and making them more and more precise, obviously, they look very random. And if you can imagine, there's many lines and there's seemingly in random places. And they're in different places for different elements. And naturally, people try to find ways to put order into this huge pile of chaotically seeming information. And so people started noticing regularities. And in fact, they started noticing regularities first for the simpler atoms. Okay, the spectrum of hydrogen was the simplest one to understand because hydrogen was the simplest atom to understand. And in fact, at first, these were empirical rules that people used to describe what was going on. Okay, there's a line here and so on and so forth in a certain progression. And then eventually people tried to go beyond simply describing what they saw and to try to explain it or describe it, based on more foundational principles. And this is then when people tried to see if either, Thomson's model of the atom or Rutherford's model of the atom, in the way that they claimed electrons could move and such, could explain that. And that was also when Bohr and all the quantum mechanics stories started, because they found that with none of these ideas, they could really explain where these spectral lines came to be. And so quantum mechanics and the Bohr model of the atom is sort of very much a product of people trying to understand that experimental data that they could gather in a very, very precise way.
So Rutherford didn't really know that much about the electrons around it. He didn't really get into that part. You just said, oh, there's a nucleus.
Sorry, which?
He didn't know much about, he didn't have any idea about orbitals around
the Thomson?
Rutherford?
Ah.
Of course not.
So, right, yes, partially. So Rutherford had the idea that there are...
He speculate about that.
Yeah, he did speculate about that. At the beginning, it seemed sort of fine to have electrons in orbitals, right? You can imagine having a small little solar system inside, right? People knew about orbital mechanics and about how planets move around the sun, so why couldn't you have the same here, right? It doesn't sound absurd to suppose that, what today we call an orbital is literally just an orbit, as in the orbit of a planet, and those electrons, they move around the nucleus, that is the sun, if you will.
The idea that the electrons would have to spiral into the nucleus.
So, right, very good. But that, very good.
You had the other principles involved.
Exactly. So in fact, what turned out to be the case, and that's a consequence also of Maxwell's work, that, these electrons, they are not at all like planets that could keep on circling forever, because what electrons do when they're sort of bending, or when they're being accelerated, if you will, they emit electromagnetic radiation. In fact, that's the same principle that is behind ultimately the formation of the X-rays. These electrons hit the end of the tube, get stopped in the glass, so they feel a huge deceleration, they emit electromagnetic radiation, which is exactly what the X-rays turned out to be. And so here, this was a big block in the road for that idea, because if you had these electrons internally spinning around, just like planets, they were supposed to emit constantly electromagnetic radiation that you could measure outside the atom, and you didn't. But more importantly, if there were indeed electromagnetic rays coming out, they would carry away some of that, if you will, orbital energy inside the electron, and so the electron would not remain on that path forever. It would, spiral around in smaller and smaller circles, and eventually crash into the nucleus. And then, of course, all claims of stability in the atom go through the window. So that was a big problem. And that is, a problem that was ultimately solved by the idea of quantum mechanics. And the idea of quantum mechanics here was, in a sort of seemingly ridiculous way, it says that, yes, sometimes particles do emit radiation when they're being accelerated, except if they move on exactly defined paths. Okay, in this case, they're stable and they do not emit radiation. Okay, but there is no sort of classical way of understanding that. It's sort of forced on you by quantum mechanics, but only by quantum mechanics. And so this is then ultimately what relieved that paradox that people for a very long time were very puzzled by, because it was a fundamental problem. It wasn't some little detail here and there. It was a fundamental problem that nobody had the answer to until quantum mechanics came around.
And you couldn't have matter like we have.
Yes.
You had those
No chance.
principles.
Absolutely. Yes.
When they were evaluating or studying the alpha, beta, and gamma radiation, did they see any kind of properties with polarization?
Very good. There was some, so it depends on what time period you're looking at. So polarization was something that was first noted for light, because light could be readily experimented with. And people noted that a light ray propagating in a certain direction is not the same light ray. There can be different kinds of polarizations of light that look the same, but you can separate them in certain experimental ways. Now, polarization in principle, that's what we know today, is also a property of gamma rays. They can be polarized. But you can imagine, experimenting with gamma rays is incomparably more difficult than experimenting with light. Because gamma rays, they just don't stop. They go right through. And it's very difficult to sort of manipulate them experimentally, right? Because, what does it mean to manipulate a light ray or to polarize them? You have to somehow make that light ray interact with the apparatus that you use to polarize it. And if everything just goes right through your apparatus and doesn't even notice the apparatus is there, then how should you, experiment? So today we know that, gamma rays can be polarized because today, we have some experimental evidence for that fact. But even more importantly, maybe, is that today we understand gamma rays as nothing else than a certain limit of electromagnetic radiation. Okay, imagine in Hertz's world where you had, his waves that he, literally, walked, past, step by step, and he saw that the wavelength was around a meter in his case, to then light, and Maxwell realizing that light was also electromagnetic radiation with wavelengths of around a nanometer. So here, gamma rays in the end turned out to be just the same as light, but again, much, much shorter in wavelength. So since we know that light can be polarized, and since we know that gamma rays today are just like light, just in a different manifestation, they can also be polarized. In fact, today we can measure polarization in gamma rays, but it's very, very hard. And then later on, so beta rays, when quantum mechanics came around and people started doing experiments, on that front, they discovered that also beta rays could be polarized, but in a different way. Okay, that would not be, if you will, an electromagnetic polarization, but it's called a spin polarization. So there's some property to that electron that is sort of the equivalent of polarization in light, but it's also different because electrons are massive and light is not massive. Yes? Yes?
Since we know so much about orbits and levels and sublevels, why can't the element that would produce the island of stability be calculated?
It could be, in principle. So let me take a step back. So the question is about stable and unstable atoms. And the question hints at the following fact. If I look at the periodic table, light elements, they tend to be at the bottom left. Okay, there's the part that I've cut off. Hydrogen, in fact, is in the top left corner as the lightest element. So light things are up here in the top left, and heavy things are down here at the bottom right of that element. So now we know that all of the radioactive elements are down here in the bottom right. Because they're so heavy, they have a tendency to decay into smaller and more stable atoms. Now you can ask a question. What if I, imagine making my elements heavier and heavier and heavier? Do they get shorter and shorter and shorter lives because their intention is to decay quicker and quicker and quicker? Or do I at some point end up at an atom that's so large, or a nucleus that's so large, that it becomes stable again? Because the forces of how the nucleus is sort of kept together have that intriguing property that, there could be something that's stable. At the moment, people don't know. Of course, you can calculate, assuming you know perfectly how all of those neutrons and protons interact and how they move and such. You could, in principle, extrapolate and see, at what point and at what circumstances you would have something that does not decay. The problem is, down here, where things are extremely subtle, and the line in between something that's stable or relatively long-lived and something that's disappearing and decaying in a split second is extremely narrow. So you don't have a lot of wiggle room, so to speak, and everything has to be exactly correct to make that atom stable. And today, we just don't think we know the laws to such a precision that would allow us to confidently extrapolate. Okay, you can speculate, but you cannot sort of confidently say, okay, here's a recipe of what I have to do, and then it will be stable, right? This, requires a lot of confidence. And, it turns out that these nuclei of very, very heavy atoms, they're extremely complicated objects because of the following. If you want a large nucleus, you had to have many protons and neutrons. But we also know that all of those protons and neutrons are at a very, very small spatial location because the nucleus is quite small. And so you have a lot of things going on in a very, very small room. And it's just very complicated because every single neutron sort of feels the existence of all the other neutrons. And every single proton feels you see, and so everybody talks to everybody, and it's a lot of chaos, right? And so everything has to work exactly out. Has to work out exactly right. And so today we don't have the tools to really confidently predict what is going to happen there.
Would that be something quantum computers could help us solve someday?
Potentially. Potentially. The reason why I say potentially is that in principle, this is a problem of quantum mechanics. Okay, describing what's going on and predicting what's going on in principle is something that quantum mechanics knows how to do. So it's not that we don't know the laws, it's just that applying them in such complicated scenarios is not trivial. And it requires a lot of computational effort. And our current computers, and that also has something very deep to say about why quantum mechanics is sometimes so difficult to work with, our computers at the moment are not really capable of running these large calculations. But if you could, and that's the idea behind quantum computing, if you could have a different, if you will, physical system that sits over here and that you can build in the lab, and you can arrange it such that it behaves just like the nucleus, it would not have protons, it would not have real protons and real neutrons, it would have some analog of those, and they would fly around in the exact same way as the protons and the neutrons in the real nucleus would, then you could use that if with lab replication of a real nucleus to see and make predictions about what happens. So this is how, but that system would have to be a quantum mechanical system, right? Because you can have a quantum mechanical system imitating another quantum mechanical system. And that's quantum computing. And
what's the best guess right now what element that would be, since we can only go up to 137?
right, it's way down here. I don't remember the exact number. It's way down here. Yes.
Maria Mayer, she was the one who first did stability in nuclei. It's on the outside.
Yes.
there on the wall.
Yes.
And on a very simplifying assumption, she got the magic numbers for nuclei like they are for chemistry, 288, that sort of thing. And I don't remember what they are, but she was right about the nuclei we do know are stable. And that's what she got the Nobel Prize.
Yes, for some of them, yes. So for the ones that we can study in the lab, we have ways to really go there. But I mean, is there an end to the periodic table? Right? So is there, and that's sort of the origin of that question, if you keep going to beyond of the atoms that we know today are stable or quasi-stable, will it be unstable forever, or will there at some point be again an island on the other side of that ocean of instability?
Very relativistic.
That's we don't. That's why it's so hard. Exactly. That's why it's so hard. It's everything at the same time, and that makes it so hard.
Yeah, Richard Feynman
Yes.
proved there can only be 137 elements. If
Ah.
you go to the 138, it would violate
But that's
Einstein's equation.
it would. So that's another question. So that has to do with the fact that relativity comes into the game, and that number 137 has to do with the strength of electricity. Okay, so that means because electricity has the strength that it has, and there's this number 137 showing up in the strength of electricity, that same number 137 also shows up as the atomic weight, sorry, the atomic charge of an element where some new effect would come into play. Okay, that's what Feynman said. That's a Feynman. That's right. Yes.
Going back to the Curie's chemical experiments, polonium. My memory is polonium is very, very short-lived.
Yes.
And you're describing they isolated it versus isomerated it.
Very good.
How did they isolate polonium before it just disappeared again?
Excellent point. So, in fact, it's true. Polonium is different from radium in the sense that polonium has a half-life, I think it's 200 days or so. And I said that it took them several years to really extract substantial quantities of radium. And several years is a lot more than 200 days. So by the time they were through, most of their polonium would have decayed away again. And in fact, they didn't manage to purify polonium. They did manage to do so for radium, which has 2,800 years of half-life. But polonium, they could only, that they knew it was there because again, they could look at its spectra. But it would not be the spectral lines, but it would not be the spectral lines of pure polonium, but it would still be embedded in a lot of other atoms that they didn't manage to separate to that extent. Okay, so polonium turns out to be a lot of a harder nut to crack than radium. And that's
They never had an ampule.
no. Yes.
Could you give us a short, simple definition of quantum mechanics?
Very good. So there's about 10 different short ways of how I could define quantum mechanics.
What's yours?
So my favorite way of doing quantum mechanics is the following. Okay, think about probability. Okay, so we know probabilities, if you roll a dice, right, you can get 1 out of 6 numbers. And if you throw it, 5 times, chances are you get 5 different numbers. So each number on a dice has exactly a probability of a sixth of appearing. Because if you roll the dice 1,000 times, roughly, a sixth of the cases would turn out to be 1. Okay, a sixth would turn out to be 2, and so forth, if the dice are not rigged. Okay, assuming that the dice are not rigged. So probabilities is something that is very intuitive to us, right? The weather tomorrow has a certain probability of it raining and so forth. It's something that we can grasp. Now, quantum mechanics is almost like probability, except for one way. Okay, so probabilities have the fact that they need to sum up to 1, right? If in that dice, if 1 has a chance of appearing a sixth of the times, and 2 and 3 and 4 and 6, if you added up all the probabilities of getting any number, you better had to get a probability of 100%. Okay, otherwise something is wrong. Because the probability of getting any number on a dice throw is 100%. You certainly get a certain number out, right? So probabilities are just numbers that we can reason about. They need to sum up to 100%. And in the world around us, we have probabilities in many places, right? Throwing dice, the weather, whatever. Something has a probability of occurring. Now, quantum mechanics is almost like probability, except in the way that the probabilities that play a role in quantum mechanics, they're not called probabilities because they're not quite, but almost. Okay, so quantum mechanics is like a weird way of reasoning about probabilities in a way that they don't have to add up to 100%, and in a way that they are not really like the numbers that we are used to, but the probabilities there are like weird numbers. And if you square these weird numbers, sometimes you get negative results. So quantum mechanics is a very prescriptive mathematical scheme of how to think about the world that has close correspondence to probabilities, in also the sense that you cannot tell me if I throw that pair of dice now, what number do I get? You can give me probabilities for what number I should get. Likewise, quantum mechanics cannot make definite predictions. It cannot say, okay, if I do this experiment in that way, this is exactly the outcome I will get. Quantum mechanics can only tell me this is the probability you will get that outcome, and this is the other probability you will get this outcome. So this is what quantum mechanics can do. It reduces what we are able to predict about the future. We're not able to predict certain outcomes. We can only say what are the chances of that outcome happening, or this other outcome. But then the more mysterious part of that is the way in which quantum mechanics arrives at that probabilistic prediction is through sort of a very weird and non-intuitive road. Okay, it involves things that are not probabilities, but that almost like probabilities. Okay, so that means if you have an experiment that you start out and you prepare it in a certain way, just like the Curies had their capacitor charged and so on, and then you saw and you tried to think what quantum mechanics would tell you about the future of what happens, okay, the electrometer needle reading a certain value and so forth, the way in which quantum mechanics would predict the probability of the needle reading this or the probability of the needle reading that would involve, in a sense, all the possible ways that the experiment could have gone. Okay, so all the possible ways, if there is, a certain way in which the needle could read 5, and there is another way in which the needle could read 5, the probabilities would have to add up. If it's 5% likely to go through this trajectory, and if it's 5% likely to go through that other trajectory, but end up in the same place, you would have a 10% chance, right? Now, in quantum mechanics, it's almost like that. You have to consider all of those different paths. All of them are important, except that some paths, they can also cancel each other out. Okay, so if it's 5% likely to go along this path and 5% likely to go along the other path, it's possible in quantum mechanics that it doesn't happen at all. Okay, which doesn't make sense. And that's exactly that difference that makes it so different from probabilities.